Hi everyone, welcome to the second episode of Workflows4s DevLog. Today I want to talk to you about parallel flows. So, parallel flow is basically the ability for a workflow to execute a couple of branches in parallel. And no, it doesn't have anything to do with performance. In the workflows domain, this is purely a logical split, allowing us to either wait for two signals in parallel or some signals at a time. And why do we do that? To not enforce any particular sequence order of events. So I have an example here. As you can see, we wait for a legal approval, manager approval, and give some feedback time before continuing. And those things might happen in parallel. So we don't want to say legal has to approve first or manager has to approve first. And this is exactly what we try to allow with parallel flows. Cool. So let's see how this was implemented. Implementation of any new element of Workflows4s starts with the WIO data structure, where we have to introduce the new variant. In this case, we introduced a WIO parallel. How does it look? It has a sequence of elements. This will be our paths. It has an ability to form the output from the results of separate paths, and it has some interim state, including the initial one. And for now, it might look a little bit cryptic. I promise everything will become cleaner in a second. So what is the element? A single path is a wheel of some in, out, and handling also interim state. So alongside the wheel, we have this function incorporate state that takes the interim state and the current state of this path and produces the interim state. This is meant to handle all the state updates of a particular path. So imagine on our previous example, give me a second. So now imagine this completes, the handle legal approval completes, and we want to modify the state. So we'll have some kind of interim state that now gets updated with that. Okay, maybe that's enough for now. Let's look how we can build that structure. So in Workflows4s, everything has a builder to make it easier to create instances. So we need to find the parallel builder. And it's defined like that, but it's probably easier to look into how it's used. So let's take a look at the parallel example, the one for the docs. So we say that we create a WIO parallel taking some initial state with the interim state being my state. And then we continuously add elements. So we add element, do A, and incorporate with the interim state counter, and added to it the path state counter. And then we have do B as a separate path where we subtract the counter from the path state from the global state. And at the end, we have to produce the output of the whole element, of the whole parallel element. And this we specify here. So we take the A out, B out, and return the counters multiplied. That is quite simplified example. what is important is that those two could have completely different result types. So if we look here, and we could say this is an int, this is a string, and it won't compile because of the bound in the implementation. But basically here we would have, if we make it right, we have int and string. So we are able to type safely compose, collect the results of all the paths when we're finishing. So let's look into how the builder is implemented. And there is the pattern of nested steps visible in all the builders in Workflows4s. And the only interesting part here is this with element. So we have a type parameter here, which is our output accumulator that inherits from a tuple. Whenever we add an element, then we append the element to our list. But what we also do, we add the tuple, the element to the tuple. And then the producing output takes the function from the tuple. So this leverages the Scala3 improved tuples that in Scala 2 would have to be an hlist. There is a hack, small hack here. So as you may notice, on the underlying data structure, we have a function from sequence of states to an output. And that's for simplicity's sake. This just makes things simpler on the implementation side. And it's safe enough because although we do have to make a cast here, it's safe because we know for sure that the elements match. So what we do here is we create a tuple from the array of all the states and cast it to our expected tuple. As long as there are no bugs, this cast is always fine. Okay, so that being covered, we can look into how this new data structure is evaluated. So as you may notice, as you may know, the Workflows4s has at least a couple of different evaluators. Those are basically instances of the interpreter pattern where we traverse our data structure to produce some particular result. And yes, there is a bunch of them. Let's look into how they work. We can start with run IO evaluator. And here, so this evaluator is used whenever we want to execute a side-effecting operation on a workflow. The input is the current state, the current time, and the IO, and the result is the event option of IO event. So if there was something to execute, then we have a side effectful operation producing an event that has to be persisted. So in case of parallel, we just go through all the elements, all the paths, and run the first one that has to run. There might be different strategies to handle that, but for now, this is simple. It works. It will run one side effectful operation, produce an event, and then the runtime can decide to execute another one from the same path or a different path. That's pretty much it. Then let's look into the signal evaluator. Signal evaluator is used when we want to deliver a signal to a particular workflow. Similar input, the signal definition, request, IO, and state. And when we hit the parallel, we do the same thing. We deliver the signal to the first path that can handle it. There are some trade-offs here or alternatives. But for now, once again, this is simple and good enough. There is a get wake up evaluator. So this traverses the structure and figures out what is the next time that the workflow should be woken up. In parallel, we take the wake ups from all the paths and then take the minimum one, meaning the one that is closest to the current time. For the get state is just a traversal that gets the current state of the workflow. And here, this gets a little bit more complicated. So we start by taking the state of all the paths. And if there was at least a single path started, because this returns an option, if at least a single path started that executed something, then we construct the initial interim state, and then we fold over all the substates that happen on some path by incorporating them through the function that we have seen. Okay. Another one is execution progress evaluator. So here we want to extract the current execution progress, and on parallel we define, like, for all the elements we get the progress of all the elements. Debugging evaluator, so the one that produces the textual output. Nothing too crazy here, just added a variant, and that's it. It's not even it doesn't follow the same patterns of other evaluators, because this is much simpler and can survive with a row pattern logic. And for last, I kept the event evaluator, because I think this might be the most interesting one. So the event evaluator is something that we execute whenever we process an event. So what has to happen on the parallel path? This is the behavior of the event evaluator is shared between this one and the proceed evaluator, which is similar to run.io, but runs without side effects. So we have to make one more jump. And if we scroll down, here we have the implementation of the logic. Let's dive into it. We need to pass the event to the first branch that can handle it. And we do that in a mutable way. Maybe there is a immutable way is probably possible, but this implementation was just simpler. So we keep a reference to the currently handled branch, its index, and what was handled. And then for each of the paths, we check if we handled that event already. If we do, we just ignore it. If we didn't, then we try to handle it. This function basically passes the event to the WIO associated with particular path. And if we get a result, we save it to our mutable reference, and we copy it into the element, because the result gives us the new WIO. This is related to progress tracking. Doesn't matter that much. Now, if after all of that we didn't have any result, then we simply say that there was nothing produced here. Now, what we do here is we look for the result of the updated element. So when we were executing that, we were updating the elements. So now we traverse them, and take their output. This is what as executed does. If we go into definition, it just gives us the option of view executed, which is a special variant that captures the output. And then we traverse using the output. The output itself is what is an either of error or output. So each of the paths could have produced an error or a valid state. Through the traversal, double traversal, we get either an error or a sequence of option of the workflow state. Now we want to return a new view that has our new parallel element stays in place. It just we update the elements of it, and then check what were our main states. If one of the paths produced an error, we complete the execution with an error. If this was right, so we received a sequence of option of state, this means we have to check if we got all the states. So if we have only present values in that place, we do this through the sequence operator from cats that gives us the sum and the list of all the states if all of them were present. And in that case, we say that our work we have a completed execution. This is a bug, or can be improved, I believe. Yes. So we say we have a completed execution with that updated element and that result. Here we invoke the form results function that is inside the view. And if we didn't get all of them, we just say that execution was partial and the element stays in place. If you wonder what is those methods, there is nothing overly complicated here. We just create some small ADT, and the complete variant contains this view executed element. So whenever element is executed, we wrap it in this executed variant and capture its state. This gives us the ability to later inspect the progress. Cool. So we've seen how the new parallel element is handled in various cases. Now we can take a look into something different, which is the renderers. And we have two. We have the BPMN renderer and Mermaid. Let's start with BPMN. So now, if you look for the parallel, what we do here is we are using Camunda model API, so the code is not pretty, the API is mutable, but it is what it is. So we start by creating a parallel gateway, capture it AD, and then we fold over the elements capture in the model. For each of the elements, we move to the gateway. That's how the API work. We say that the current state, the current pointer points to the gateway, and then we handle that branch. This will basically add all the elements to as a children of that parallel gateway. And at the end, if we have the end gateway, we connect the result to it, and if we don't have it, we create the parallel gateway. This will happen on the first path, and that's basically it. At the end, we move to the end gateway. So it might be a little bit more complicated. It gets easier when you know how the BPM and library works. What I can show you is how this looks in practice. So this is a parallel gateway in the BPMN format. So we render the first path, create this. We don't have the end gateway yet, so we create this, and then we start processing the second one, move here, render this, and then we already created the end gateway, so we just make a connection. Okay, now the Mermaid renderer. And here, the implementation is a little bit different because we don't use external API, we use a state monad instead. And what happens here? We start by adding a step with some random ID, and in shape of the fork, this comes from Mermaid. Then if that model has started, we have a function to detect that. We mark the fork as executed, other we don't mark it as anything. Then for each element on the list, we set the active nodes to the fork, we render the element, and then we capture the endings of the flow. Rendering can have multiple active nodes at the end. So we capture them, flat traverse, so we have all the endings collected here. And then we make a connection from those nodes to a new step. This once again, a fork shape, handled in the same way. And the result of that is parallel Mermaid, which looks like that. If we take it to the UI, it's basically this. So we created all those shapes and then connected them to the file. Okay. That's almost all I wanted to show you. But there is one more thing that I wanted to share, because with that development, we also improved a little bit the testing infrastructure. So historically, testing required quite a lot of boilerplate. This boilerplate might still be visible in some of the tests that were not yet migrated. I don't know which one that could be. But now we have a test utils that allows us to create the different elements of the workflow from predefined context, predefined state, that help write the tests. So when we test the parallel flow, we create the two steps, both pure. In this case, step 1, step 2. We create a parallel. This is just a helper function that adds those two VOs to the parallel. It sums their states. We create the instance query for its state, and then verify that the result has all those steps executed. How it works is that the test utils rely on our test context, which has a state that basically collects all the executed steps IDs. So with that, the tests are quite clean and easy to follow. And that's it. This is how we implemented that. Thank you for listening, and see you in the next episode.